A cup of coffee seems like one of the least mysterious objects in your life. You pour it, lift it, sip it, and if you wait too long, it disappoints you. The heat fades, the surface cools. What was once rich, fragrant, and almost alive with warmth becomes flat and lukewarm. Most people treat that as a minor annoyance, the price of distraction, nothing more. But hidden inside that ordinary disappointment is a question far deeper than it first appears. Where did the heat go? At first, the question feels childish, almost too simple to matter. The coffee was hot, now it is cooler, so obviously it lost heat. That sounds like an explanation, but it is really just a restatement. It tells you what happened from the outside, not what actually took place. Because the moment you ask where that energy went, the scene stops being trivial. A cooling cup of coffee becomes a small window into one of the most powerful laws in physics. What makes this so strange is that energy is not supposed to vanish. You may have heard many times that energy cannot be created or destroyed. If that is true, then the coffee's heat did not simply disappear into nothing. It went somewhere. It changed form, moved location, spread out, or became harder to notice. But whatever happened, it was not magic. The warmth that once sat, concentrated in that cup, did not break the rules of nature. It obeyed them, and that is exactly why the question matters. Because what you casually call cooling down is not a tiny domestic inconvenience. It is a visible example of energy changing from something concentrated and useful into something dispersed and difficult to recover. The coffee begins with a kind of energetic privilege. Its molecules are moving more violently than those in the surrounding room. That difference is what you feel as heat. It is what makes the cup comforting in your hands, and the first sip almost shockingly alive. But nature does not like concentrated differences to remain concentrated for long. This is the part most people never stop to consider. Your coffee is not just getting colder, it is surrendering a temporary imbalance. It is participating in a universal drift, a quiet process by which energetic order spreads outward and becomes less available for purposeful use. That sounds abstract, but it is happening right there on your desk while you answer an email or stare out the window. The hot coffee and the cooler room are not equals. One contains concentrated thermal energy, the other does not, and the universe has a clear preference about what happens next. The concentration softens, the difference shrinks, the heat moves outward, not because coffee is weak and not because warmth is fragile, but because this is how the physical world behaves when left alone. So the next time your coffee cools before you finish it, do not treat it as merely bad timing. Treat it as evidence. Something profound is happening in plain sight. A humble cup is revealing that loss does not always mean disappearance. Sometimes it means dispersal. Sometimes it means the world taking something vivid and spreading it so widely that, for all practical purposes, it is gone. The most important mistake people make about a cooling cup of coffee is imagining that the heat somehow drains away, as if the coffee were a battery slowly emptying into nothing. But that is not what is happening. The coffee is not running out of energy in the sense of losing it from existence. It is transferring thermal energy into everything around it. What feels like disappearance is really distribution. Heat is not a substance hiding inside the coffee like water in a container. It is a way of describing the restless motion of molecules. In a hot cup of coffee, those molecules are moving, colliding, vibrating, and rotating with greater average energy than the molecules in the cooler air around them. That difference matters. Whenever two systems at different temperatures are in contact, energy tends to flow from the hotter one to the cooler one. Not because of intention, not because the coffee wants to cool, but because this is the statistical behavior of matter itself, and the coffee has many ways to surrender that concentrated heat. Some energy leaves through conduction. The hot liquid warms the cup. The cup warms your hand, the table, the surrounding air. Molecules jostle their neighbors, and that extra motion passes outward through contact. Some energy leaves through convection. The air touching the coffee warms up, becomes less dense, and rises away, carrying heat with it while cooler air moves in to replace it. Some leaves through radiation because all warm objects emit electromagnetic energy, mostly in infrared wavelengths, into the environment around them. And some leaves through evaporation, which is even more dramatic than it appears. The fastest moving molecules near the surface escape into the air as vapor, carrying away a disproportionate share of thermal energy and helping cool the liquid that remains. None of this is exotic. It is happening constantly, all at once, and usually invisibly. The cup, the spoon, the countertop, the air in the room, even the walls nearby, are all participating in the process. Your coffee is not isolated. It sits inside a world ready to absorb every temperature difference it can. If you place a lid on the cup, use a thicker mug, or wrap your hands around it, you slow some of these pathways, but you do not abolish them. You are only reducing the rate at which the temperature difference collapses. Given enough time, the coffee and the room still move toward the same thermal balance. Hotter and colder do not peacefully coexist forever when matter and energy can still pass between them. That outcome is built into the setup. That is why the phrase, "the coffee lost heat," is both true and misleading. It is true because the coffee becomes cooler, but it is misleading if it tempts you to imagine that the heat somehow ceases to exist. The better description is that the thermal energy becomes less concentrated and more widely shared. What was once gathered into one small cup spreads into the room, the furniture, the air currents, the invisible infrared glow of warm surfaces, and the water vapor rising from the top. From your point of view, this feels like loss because the energy is no longer where you want it. It no longer sits in a useful, concentrated form waiting in the cup. But physically, the universe has not thrown it away. It has simply diluted it into its surroundings. And that dilution is the beginning of a much deeper idea. Because once energy spreads out like this, something important changes. The problem is no longer whether the energy still exists. It does. The problem is that dispersed energy is harder to gather back into a form that can do something meaningful for you. This is the part of the story that feels almost unfair. You are told correctly that energy is conserved, that it cannot be destroyed, and yet your coffee still ends up cold. The heat is still somewhere in the room, still present in the air, the cup, the table, and the moving molecules around you. Nothing has vanished. And yet, from any practical point of view, something very real has been lost. What has been lost is not energy in the absolute sense. What has been lost is usefulness. That distinction sits at the heart of thermodynamics, and most people never really encounter it. We speak about energy as though all energy were equally valuable, equally available, equally capable of doing something for us. But it is not. A hot cup of coffee and a lukewarm room may contain the same total energy after enough time has passed, but they do not contain it in the same form. One contains concentrated thermal difference. The other contains a much broader, more evenly spread distribution. And that difference between concentrated and spread out energy is the difference between power and irrelevance. When your coffee is hot, its thermal energy is organized in a useful way. The liquid is much warmer than the surrounding air, which means there is a temperature gradient, a difference that can drive change. That difference is what warms your hands when you hold the cup. It is what sends fragrant molecules upward into the air. It is what gives the drink its immediate, vivid sensory force. The energy is not just present, it is available. It can flow in a meaningful direction and produce noticeable effects. Once the coffee cools, much of that possibility is gone. The energy has not been erased, but it has been diluted into the environment. The room is now microscopically warmer than it would have been otherwise, but not in any way you can gather back into the cup without extra effort. This is why dispersed energy feels like lost energy. In principle, it still exists. In practice, it is no longer concentrated enough to matter. A useful way to think about this is money. Imagine all your wealth is handed to you as one solid, spendable sum. You can act with it. You can direct it. You can use it to change your situation. Now imagine the same amount is broken into microscopic fragments and scattered across an entire city. The total amount still exists, but it is no longer functionally yours in the same sense. Recovering it would cost more than it is worth. That is what happens to the heat in your coffee. The energy is conserved, but its practical value collapses as it disperses. Physicists often describe this in terms of energy quality. High-quality energy is energy arranged in a form that can do useful work. Low-quality energy is energy that still exists but is too spread out to be harnessed efficiently. A hot object in a cool room contains higher quality thermal energy than that same object after it reaches room temperature. Not because the total energy suddenly became unreal, but because the gradient that made the energy useful has faded away. That is why a cold cup of coffee is such a quiet lesson in physical reality. It demonstrates that conservation alone is not enough to preserve value. The universe may keep the bookkeeping exact, but it does not preserve convenience, concentration, or usefulness. Those are temporary advantages, and once they are lost, getting them back usually requires more organized energy from somewhere else. So when your coffee cools, you are not watching energy vanish. You are watching it become less capable of serving your purposes, and that idea extends far beyond coffee. It applies to engines that waste fuel as heat, batteries that run down, machines that become inefficient, and bodies that struggle to maintain order. The deeper law is no longer just about where the energy went. It is about why nature so often turns concentrated possibility into diffuse residue, and why that one-way drift seems to give time itself its direction. By now, the cooling coffee no longer looks like a minor kitchen inconvenience. It looks like a physical process with a deeper message. The heat spreads, the useful concentration fades, and the energy becomes harder to recover. But the strangest part is not simply that this happens. The strangest part is that it happens in one direction. You never walk into a room and find a lukewarm cup spontaneously drawing scattered heat out of the air, the table, and the walls until it becomes freshly hot again. You never see vapor leap back into the liquid in just the right way to restore what was lost. The laws of motion at the microscopic level do not absolutely forbid individual molecules from moving in those directions. And yet in the real world, the overall process overwhelmingly runs the other way. Hot coffee becomes cooler coffee. Ordered concentration becomes wider dispersal. The future looks different from the past because nature strongly favors that direction of change. This is where thermodynamics stops being merely practical and becomes philosophical. A cooling cup of coffee is a small demonstration of entropy, the tendency for energy to spread out and for organized differences to dissolve into more probable, more distributed states. Entropy is often described loosely as disorder, but in this context, the essential point is simpler and more powerful. There are vastly more ways for thermal energy to be dispersed than for it to remain tightly concentrated in one hot cup. That statistical imbalance is what gives the process its one-way character. A hot cup in a cooler room is a special arrangement, a localized concentration of energy. As the coffee cools, the energy can spread into countless surrounding molecules in unimaginably many ways. The number of possible dispersed arrangements is enormous compared with the number of highly concentrated ones. So the coffee does not cool because nature hates warmth or prefers disappointment. It cools because the dispersed state is overwhelmingly more likely, and that likelihood is what we experience as the arrow of time. You feel time moving forward not because clocks tick, but because physical systems evolve from less probable arrangements toward more probable ones. Ice melts, perfume spreads, batteries drain, bodies age, coffee cools. In each case, the underlying lesson is the same. Concentrated order tends to unravel into broader distribution unless work is done to maintain it. The future is not just later than the past. It is usually more dispersed than the past. That is why a hot cup of coffee feels almost symbolic, even before you know the physics. It begins as a temporary defiance of its surroundings. Someone boiled water, brewed the drink, poured it into a cup, and created a thermal difference that would not have appeared on its own. But once that effort stops, the universe resumes its preferred direction. The difference narrows. The cup and the room move toward equilibrium. Time, in a very real sense, becomes visible in the fading heat. This is also why reheating the coffee does not violate the rule. When you put it in a microwave or on a warmer, you are not making entropy disappear. You are importing organized energy from somewhere else to restore the concentration temporarily. The reversal is local and paid for by a larger expenditure. Nature does not object to hot coffee. It objects to hot coffee for free. So the next time your drink goes cold, remember what you are actually watching. Not mere cooling, but a tiny, silent proof that the universe has a preferred direction, not because energy vanishes, but because spreading out is easier, more numerous, and more likely than gathering itself back together. Once you see what is happening in a cooling cup of coffee, it becomes difficult to keep it confined to the kitchen. The same principle appears almost everywhere. A car engine burns fuel, but only part of that energy becomes motion. Much of it escapes as waste heat. A laptop grows warm while performing calculations because organized electrical energy is constantly degrading into less useful thermal agitation. A house in winter leaks warmth into the cold outdoors no matter how carefully it is built. Again and again, useful differences erode unless effort is spent to maintain them. Your body is no exception. In fact, it may be the most intimate example of all. You eat food not because matter alone sustains you, but because your body needs a continual supply of concentrated chemical energy. Cells break apart molecules, capture part of that energy, and use it to build structure, move muscles, repair damage, maintain gradients, and keep the larger system from collapsing into equilibrium with its surroundings. Life is not the absence of thermodynamics. Life is thermodynamics under pressure, constantly borrowing ordered energy to resist dispersal for a while. That is why fatigue is not just psychological, and why aging cannot be understood only as the passing of birthdays. Living systems are always fighting leakage. Heat leaves the body. Molecules break down. Gradients weaken. Structures require maintenance. Useful energy must be gathered, transformed, and directed over and over again. And even when that process works beautifully, it never works perfectly. Some energy always slips into less useful forms. Some order is always costly to preserve. The body, like the cup of coffee, exists inside a universe where concentration is temporary. This does not make life pointless. It makes it remarkable. A hot cup of coffee cools because no internal machinery is actively preserving the temperature difference. A living organism, by contrast, survives precisely because it is full of machinery devoted to delaying that kind of surrender. Your heart, lungs, liver, muscles, and cells are all participating in one vast effort to keep useful energy flowing in organized channels, rather than letting it simply dissolve into ambient heat. In that sense, life is not a violation of the arrow of time. It is a local, temporary negotiation with it. Machines do something similar on a simpler level. Refrigerators keep interiors cold only by expelling heat elsewhere. Power plants generate electricity by exploiting temperature differences that cannot remain forever. Batteries store organized energy temporarily, then lose the ability to deliver it once their internal chemistry evens out. Every technology humans build depends, in one form or another, on creating, preserving, or exploiting concentrations that nature would otherwise flatten. So the lesson of the coffee is larger than coffee. It tells you that usefulness is never automatic. Warmth, motion, power, vitality, structure, and life itself all depend on concentrated differences that the universe does not preserve for free. They must be created, maintained, and renewed. And when that renewal stops, dispersal resumes. That is the unsettling truth hidden in a forgotten mug on a desk. Your coffee is not merely cooling. It is acting out the same law that shapes engines, homes, muscles, memory, effort, and time. It is a miniature portrait of existence in a thermodynamic universe. Moments of concentration briefly won, briefly enjoyed, and gradually surrendered. And perhaps that is why the sight of cold coffee feels faintly disappointing in a way that goes beyond taste. At some quiet level, you are looking at a universal pattern made visible. Energy remains, but usefulness fades. The difference that mattered softens. The world keeps the total, but not the form you wanted.